All right, you can start.
That does look good. All right. Thank you, everybody, very much for joining us again for another edition of Grease Thief Thursday. This week, we will be talking about ruler testing and how we can optimize our grease relubrication frequency in doing so. So I'm going to go ahead and turn it over to Rich and give the presentation, and at the end, we'll have our live demonstration.
Okay, that looks good then? Great. All right, thanks, Richard. So today we're going to talk about the ruler technology. Ruler being an abbreviation for remaining useful life. It's a technology that's been around for a long time. I had one of the original units in the power plant where I worked, and it was probably in the mid-1990s when it was literally a black box and not much else. But it's come a long way, and in addition to having that history of being able to evaluate antioxidants, especially in, let's say, turbine oils and other large reservoirs where we use it as a tool to be able to get the maximum life out of those oils. We've started using it more so for greases. And that's what I'm really going to focus on here today. The ruler as a tool to monitor antioxidant formulations in greases for lubricant optimization. And so what is the ruler? That's kind of the commercial abbreviation for the scientific term, which is linear sweep voltammetry. And that analysis provides a way of quantifying individual antioxidants, isolating them, and giving a relative level, and it's relative to the starting point, or basically what the formulation is in the new oil or new grease. This allows us to understand how much oxidation resistance is still in that lubricant after some period of time in service. And then if we do that routinely check that, we can trend that level and kind of predict what's happening and how much time we have to go, let's say in a turbine oil, before we'll get to a very low level and lose that protection. Greases, it's a little bit different because greases are being replenished at some frequency. And as I'll explain, we're going to be looking at greases at or near the end of their cycles in most cases to see, are we truly optimized? So this is analysis that can be performed by a laboratory, as you'll see here today, or on-site, fairly portable instrument as well. So why would you run ruler on greases? Well, this analysis will, like we said, compare the baseline to a grease that's been in service for some period of time. Typically, we have access to that grease when it would be at the end of the anticipated service. In other words, when we're going to go in and pump new grease in there and push the old grease out. And ideally, that grease is right at the end of its life. It's been in there long enough. It has resisted oxidation. It has not accumulated debris, particulate. It's not broken down. It's not physically broken down, such as consistency has changed and so forth. But that's not always the case. And so the grease intervals that we use are often based off of a time schedule. Once per month or once per quarter or what have you, someone will go out with a grease gun, pump new grease in, and push the old grease out. Or it might be an auto-luber system, and that auto-luber system would be programmed, and there would be some periodicity of an amount of grease that's added on a timer. And if we can take a sample of that grease, where we're looking at it near the end, we understand what's happened. Now, that time-based schedule is often what is the default situation. And sometimes it's extremely default, like once a quarter, just lubricate everything, pump grease until it comes out somewhere. That's obviously not ideal. Other folks have gotten more precise with determining those intervals by using calculations and pretty broad engineering assumptions about what that particular application is and how it's stressing the grease. Other folks will use ultrasound, and there you're listening for bearing film starvation. So you look for the ultrasound levels to jump when you no longer have sufficient grease present. And all those steps are better than nothing, and they're improvements along the way. But we're looking to truly optimize the grease, and say, is the grease truly at the end of its life? If it is, that's when we want to change that out. So if we were to take a sample, and it's at that frequency that we had already determined from a time basis, and it's at the end of what we believe the life is, but yet there's still significant remaining antioxidants in the sample, then it's maybe possible to extend that frequency, and that's what we're really looking at. So lubrication degradation defines the failing point of the grease. Obviously, we don't want grease to be in service until it fails and then causes damage to the equipment or interrupts service. We want to get to it before that point. So if we do regular grease sampling and analysis, we can help to establish the trend data. We can have a targeted understanding of that equipment based off of the realities, not just assumptions, but realities of the stresses and contaminant streams and other things that will push that grease to the end of its functional life. Grease analysis using this standard, this ASTM standard D7918, does include ruler testing, and it can show if the lubricant is in good condition at the end of an established interval, and if so, then that interval can be extended. If the lubricant has no antioxidant protection left at the established interval, then the grease is dying while it's still in service. And that lubrication frequency should be increased manually or by changing an automated lubricator settings to optimize so that we're changing out that grease before it gets to the end of its life. Of course, there's other factors. It's not all about oxidation. We may want to replenish grease on a frequency that before we get to the end of oxidative life because of contaminants in the environment. So we're using grease to purge out those contaminants. So in that case, our analysis should include roller, but it should also include contaminant analysis, things like particulate monitoring, markers of the contaminants in that area, like silicon, if it's sand or dust. Also looking at consistency changes to make sure the grease is holding up. Maybe it's not oxidized yet, but it's gotten very soft and it's going to run out of that bearing, or it's gotten very hard and it's no longer coming in contact and lubricating the surface. So these are all analysis things that we want to perform in addition to the ruler for antioxidants to determine what is that end of time and that end of life. Grease lubrication optimization is going to use quantifiable data, not just assumptions about the stresses that this grease will undergo in service. So this allows the user or a laboratory to monitor and change lubrication maintenance intervals to replenish the oxidation in time and optimally to prevent excessive oxidation of the grease and degradation of performance. So how do we go about this? Well, for those of us who have done ruler before, we understand that some of these considerations and steps to take. There are multiple grease test solutions, or ruler test solutions that are different colors. They're color coded. So we've got green, yellow, blue, and red. Why are there different test solutions? Because there are different chemistries involved in our antioxidant packages. And these colored solutions are optimized for those different chemistries for the extraction of the antioxidants into a solvent phase. Once they're in that solvent phase and separated from the oil and the contaminants and everything else that is there, we create this titration capability. It's a changing voltage titration, if you will. So we have that linear sweep voltammetry, which means we're going to sweep the voltage through a range, and as it sees the corresponding current flow, which will happen at the specific voltage to the behavior of that additive, we'll see the current flow as an indicator of how much is there. So by where it comes out in that voltage sweep, we know what kind of additive it is, and how high the peak is in terms of current flow, we know how much is there. And we create a profile for that. The green solution is the one that we use for greases. You can see green, yellow, blue, and red, and they're, again, to those different chemistries, like diesel engine oils, aircraft engine oils. Some have to do with the chemistries and differences in the base oils and so forth. But you have different volumes that you can use depending on how heavily spiked, let's say, the antioxidants are in a given formulation, and we sometimes have to adjust the liquid sample values up and down, we typically use this standard 250 milligrams of grease as the amount of grease that we'll use to test. And we can either be measuring that out manually, or we'll show you how that is a somewhat automated process when we use the Grease Thief and the ASTM D7918 approach. So within the solution, you can see the different additives. Green is kind of a generic approach, is kind of the default solution to use, and you can pick up ZDDP, which is primarily thought of as an anti-wear additive, but it also has antioxidant capabilities, as evidenced by its response in the ruler test, and that would be the first additive peak that we would see. And then you will see amines and phenols selectively, and you see it written in seconds because it's, again, it's a voltage sweep. So the longer period of time from the start of the test, the higher the voltage is going, or the voltage is changing, and that changing voltage corresponds to these different chemistries, the ZDDP, the amines, and the phenols. So yeah, and you can see which order they come out, and it really depends on the chemistry and the test solution and so forth. But we stay focused on this green solution. And what we find is in most greases, we see 1 or 2 peaks. Sometimes you see 3. I know Yoameya has shown me some graphs of where he found 5 or 6 different peaks in greases, meaning they're blending different additive chemistries, different amines and phenols, and probably ZDDP in there as well. So you just really don't know what you're going to find until you characterize that new grease and know how many different peaks are characteristic of that antioxidant package formulation. But that's what we're going to be looking for here. And you can see this kind of represented as this linear voltage ramp as the voltage is going up over a period of time, which is somewhere around 20 seconds of total time as you sweep through that voltage. You're going to see those peaks respond for ZDDP for, you know, here's an example of an amine, phenyl alpha naphthylamine, and that's shown there. That's one of a number of different amine materials that could be there. BHT, butylated hydroxytoluene, shown there at the left. I'm sorry, at the lower right. That is also a possibility. That is a hindered phenol. You know, those who know chemistry, you'll see the phenol structure, the OH group at the top there, and then you'll see the organic groups on either side of it. That means it's hindered, it's kind of blocked, and this is a chemistry that gives us a good antioxidant response. In fact, I sometimes talk about in my training classes that as a kid, I would eat breakfast cereals, and I would, you know, read the instructions or read the ingredients on the breakfast cereals. And more often than not, maybe as a kid of the 70s, I don't know if we see it as much today, but we would see BHT or BHA added for freshness to our breakfast cereals. So when I was getting that crispy Captain Crunch, if that BHT or BHA was doing its job, I would have some fresh cereal to eat. It's curious that the very similar, if not same chemistry, can be used in lubricants to provide essentially the same kind of protection. The reason my breakfast cereal was crispy and crunchy is because it had not oxidized, and that was attributable to the antioxidant that was used in the ingredients. It is a similar chemical inhibiting process that we're using with the BHT here that you see, or the phenyl naphthylamine and what have you, to extend the life of our lubricants by delaying the onset of oxidation. So how do we get to this point? Well, first off, we've got to get a good sample. And that really underlies, you know, everything we do about analysis, but especially with greases. And so the grease sample is collected per some guidance that we have in the ASTM standard ASTM D7718. And then the grease can be extruded per the dye extrusion method outlined in D7918, and you see that on the right. So on the left, we have a picture of a soldier taking a grease sample. This is from a helicopter, and we're going to talk about this case study in a little bit. This is coming from a hub adapter. So there's little tooth splines in there. It's grease lubricated. This is a very old aircraft that's been around for over 50 years. So there's long-standing maintenance about how often do we need to take that out of service, take these parts apart, clean off the old grease, add new grease. A lot of assumptions went into the historical maintenance intervals to determine that. So what we wanted to do was say, let's find a way to get a good and representative sample. Let's realize that the volume that's available to sample that's representative is very, very small. In this case, less than a gram of grease. And once we understand that, and then we create the method and the tools to extract that sample by use of a grease thief kit in this case, then we can do the analysis. And if we have enough to extrude through die extrusion, it creates this nice thin film. So you see that at the right-hand side picture, you can see this thin strip with the yellow ribbon lying on it, and that's the extruded grease laying down in a thin film. And you're going to see that's what we're going to use to do the grease, the ruler analysis with the grease. That little that strip is separated into different sections, and they are designed so that if we get a nice smooth extraction of the grease, a nice smooth extrusion of the grease through the sizing of the exit slot, it will create a length of grease and width that creates about 0.25 grams of grease. And if you remember in that table, we showed you that our target is 250 milligrams of grease. So we're pre-creating, if you will, in an optimal configuration, being a thin film on a substrate, this grease sample, so that we can add that directly to the ruler solution. That can be shaken up, and we find that most grease formulations, this is very effective. The solvent system, this green solvent system, is very effective at getting complete dissolution of that grease sample. This is very important in trying to transfer consistently the same amount, if not all, of the antioxidants that are present. So when we compare the new grease to the used grease, we get a consistent basis for that quantification. So this method involving the 7918 and the preparation of the thin film, we put one full strip into the ruler vial that contains the solution in the sand. Now, another way you could do this is get the vial, like if you don't have a thin film strip, you might get the vial while it's still dry, and you can just kind of wipe grease on the inside of the vial. If you look at the method, the manual method, it does tell you to get that kind of on the inside of the vial as a thin film. I think that's a bit challenging, but the better job you do there, the more easily the antioxidants are going to go into solution. And that's why we prefer this method of the thin film that's consistently and uniformly extruded out on the substrate, so we don't have to worry about the variability of someone's ability to kind of wipe that thin or leave little chunks inside or what have you. So that's a difference here between the method that we use and that falls under 7918, D7918 versus a more manual approach, but both can be done, and the key is consistency. So once that's in there and it's been agitated and the solvent's doing its work there, then we want to allow a full additive release into solution. The ASTM standard that's specific for grease evaluation for ruler, D7527, directs you to wait 30 minutes before the test. We've done some studies here with different kinds of greases, and we found that while that 30 minutes does work for some greases, in other cases, we find that there is a kind of a diminishing contribution if we let it go longer, that at 6 hours tends to go to near zero. So we like to make, as part of our grease analysis process, a set aside of this vial for 6 hours so that we can consistently be confident that we get that full dissolution of the antioxidants into solution, and then it's a valid comparison back to the new grease. Now you could also make the argument that if you do 30 minutes every time, the same amount is released from the new grease and from the used grease. That might be a pretty good assumption, but when you get into a situation where your greases are aging and changing and maybe have contaminants there, maybe that cycle of dissolution isn't quite the same as it was when the grease was new. So we like to give it that 6 hour set time to make sure we fully get those antioxidant additives into solution so we can test it with the ruler. And so in a minute here, Dylan's going to show us actually the test itself, which will be good, and then we're going to go into interpreting the results. The results are about looking at the peaks. We select those peaks using the software, compare them to the reference sample, and give it as a percentage of remaining antioxidants for each of the peaks identified in the new grease. And sometimes we make some adjustments to the used sample as the shape of the peak may have changed, and we want to make sure that we're fully representing that. So here's a few examples. This is an example of a high remaining useful life. We've got a baseline here. And I guess to protect the innocent, we haven't named the product, but nonetheless, we've got some new grease here that is our standard, that is the white line. And then a sample from a machine that's been in service of the used grease is the red line. Now, you can see that there are two peaks in the baseline. There's two peaks in the used sample. These peaks do not quite line up exactly. There is what we call this spectral shift or peak shift. And you can even see a little bit of appearance maybe of a small third peak off to the left. Maybe that's our ZDDP there that we haven't really quantified in this example because it's relatively small compared to the other two peaks, which are the amine and then the phenol. But amplitude-wise, they're still very close. We get a calculated value here of 98. And there are some different reasons that we might see these peak shifts, different formulations, a baseline, perhaps some changes, other chemical changes in the solution, but they're pretty close and pretty good alignment and very high remaining useful life on this particular grease. So we would look at that and say, how long has that grease been in service? Has it been subjected to the normal forces that it will in this kind of service? And if that's the case, the period that elapsed between the new grease and this used grease hasn't really done a lot to the life of the grease. There's still a lot of remaining useful life here. And if this is our greasing relubrication interval, when we got this sample, we've got a position to extend that out pretty substantially. Here's another example that's at the opposite end of the scale where we've flat out lost it. And we've got a baseline here, a new grease. Kind of has a strange response. It looks like it's tailing up to something up there, but not really a second defined peak here, really just a single amine peak that we're finding. But when we compare that to the in-service grease, we can see it's shot. That grease has, like we like to say, it's died in the machine, okay, from an antioxidant standpoint. So whatever the circumstances were, if this is the normal operating conditions for this grease, whatever this frequency was, it just wasn't quick enough. It wasn't soon enough to rescue that grease, to replenish it, and to continue to protect that particular machine. So here's an example where we want to go back and review and say, we may have to shorten up that interval. We sometimes see this as well, which is helpful in determining grease mixing. And as a laboratory that does a lot of grease analysis, grease mixing is one of the most common problems that we see. There's several ways to detect grease mixing. We can see it through the elemental numbers compared to, let's say, knowing what's supposed to be in that baseline from an additive perspective. From a metallic additive perspective, we might look at the color of the grease and compare that, and we can see a complete color shift, which might tell us that a different color grease has been mixed in, which is not good. And we might see it in the fingerprint of the FTR, but we also might like to look at the ruler, because sometimes you get this kind of response. The white line again is the new fresh grease, and you see that strong single amine peak. But when we test this grease that's in service, you've got two different peaks, and they don't line up with this at all. So either you've got one peak here and it's shifted pretty substantially, or you have a different grease with a completely different formulation. Both are possible. This could be grease mixing. It could also be we have the wrong baseline, or what the customer thinks is in that machine is not what it's being lubricated with. So another helpful way of looking at the data and understanding the data that comes from the ruler test for greases. So I'll talk about this case study. We tested over 1,000 samples. It was a 15-month test period. These were from H-47 Chinook helicopters. And our objective here was to collect data to address flight safety. We always want to maintain high flight safety on these assets, and really any aerospace assets, of course. But we also wanted to review history to optimize maintenance tasks, and that included the greasing task. So there was some activities that were causing the helicopters to come to depot maintenance at a fairly frequent clip to address regreasing tasks. And some of this was based off of estimates or engineering input, or maybe operating history. And so this was an opportunity to look at that and get some test data to help understand that, whether it's truly optimized. We took samples per D7718. We modified existing kits slightly, created a new helicopter-specific grease sampling kit. In particular, modifications were necessary to be able to optimize the collection of the very small grease quantities present in these small drive splines, sometimes less than a gram of grease being available there. And then we set up analysis per 7918, which does reference the ruler method to the 7527, and talks about the preparation out of the die extrusion process as a thin film. Then we had to figure out, now, how do you compare the fact that the same asset is being lubricated with different greases? Now, in the military, we have something called mil-spec, and mil-spec says here are the specifications required from a performance standpoint for greases that will work in this asset. That mil-spec grease could be met by several different manufacturers. And what we found is those manufacturers use different formulations to meet that mil-spec. Therefore, you can have different greases, or unfortunately, even mixtures of greases ending up in the assets. Some of the greases meeting the mil-spec in using the ruler clearly had two peaks, an amine, a strong amine, a strong phenol response. And then you had other formulations that only had a single amine peak. So we had to create a way of comparing what was the loss of antioxidants over time. So in doing so, we created an index. We called this the oxidation index. And this was a way to value both kinds of antioxidant formulations in the study to get a weighted total value of the number 300. We got that by multiplying the quantity of the phenolic additive by 2, and then adding the quantity. And when I say quantity, I'm talking about percent remaining relative to the new grease, right? So the quantity of the amine added to the quantity or the percentage remaining of the phenol times 2. So if you had 100% of your phenol, 100% of the amine, 2 times 100 plus 100, you get 300. So basically, the starting point for that index is 300. And as greases lose their antioxidants, they would go down from that. And then for the other grease formulation that just had the amine, we would multiply that by 3. So our index became against a value of 300. That allowed us to take this common asset, which is being operated around the world under different circumstances and so forth, and see how that oxidation index would change with respect to flight hours, right? So if we have different flight hour samples being taken, we can create a graph to see how that changes, and we can even then compare greases with different antioxidant packages to see if there's some correlation and gives us some validity in what happens over time. Now, here is a plot from one of the components on the aircraft called the drive collar. There's a forward and aft drive collar. We grouped the data together because we found that it matched up very well, and it created this fairly high correspondence value on a graph of the oxidation index, which you can see goes as high as 300 off to the left of the graph, and that would be kind of a grease that was maybe brand new. And then as time goes on, you can see those values decreasing in almost a linear fashion. And so our thing is equipment hours here, which is flight hours. So we did get some samples that were almost brand new, just a few flight hours, and they had very high oxidation index, shows there was very little oxidation stress on that grease, still had that high value. And you can see now that we were able to create a line of best fit that approximated the loss of antioxidants with respect to flight hours. And when you take that fit through, we use the criteria that says, in general, you look for a change out of a lubricant when you get down to about 25% of the remaining antioxidant, right? So that tells us that we have minimal remaining protection, and we would want to replenish that, let's say, if it were oil in a turbine or something like that. Here we took that 25% of 300 and said, okay, 75 as our oxidation index is our cutoff. So we look for the value that corresponded to that. And you can see in this graph, it's about 170 flight hours. We found that the equipment was being in the field for closer to 200 flight hours on average. Therefore, this necessitated a reduction or in frequency or more frequent greasing. This was the only example that was like this. In the rest of the study, most of the locations in the aircraft were doubled in frequency. And what that resulted in was a significant increase in availability of that asset, as well as enhancement of reliability, life, and flight safety, because we are addressing the one component here that does need more frequent greasing while being able to optimize the life of other components, reducing maintenance activities, cutting the labor requirements nearly in half, and significantly increasing the time of availability for this asset in the field, because we're no longer unnecessarily greasing assets that still have remaining life. And so all that's kind of wrapped up in this graph here. And I think the thing to look at is the red blocks here. We didn't just look at oxidation. We looked at moisture, the accumulation of moisture. We looked at ferrous content and iron levels, ferrous content from normal rubbing component wear modes, iron levels for some of the smaller, say, fretting wear or oxidative or corrosive type wear mechanisms. We looked at the dye extrusion values for consistency changes of the grease, silver levels, which were surprising for us, but we did find them to be present as a coating on some of these splines, silicon levels as a tracer of sand and dirt contamination. And in doing so, we went to the limiting condition in terms of projected hours to requiring, flight hours to requiring replenishment. You can see by the red blocks that the primary driver for almost all of these was oxidation index. Therefore, the ruler became a critical tool for us in deciding what should be that grease changing interval. There were two that had other parameters. There was a transmission fan shaft that had a reduction in the consistency of the grease below a minimum value, and therefore that was the driver in terms of grease replenishment. And we had another location that was very close to, let's say, water in a water landing or other, humidity considerations. So moisture was accumulating, and that became the driver in another location. But for the most part, most of the decision was based off of the loss of the antioxidants and knowing how to and when to optimize that. So I got a slide up that says questions here, but I'm going to skip off of that for a moment. I'm going to pivot to Dylan so he can do a demonstration for us and show us how we're going to go through a greasing, a grease-based evaluation of the ruler test. So I'm going to prop this up a little bit.
All right. Okay. So when we start our ruler analysis, we're going to start with our grease that was extruded with our grease deep analyzer by ASTM D7918. So we have our extruded strip right here. And so we're going to take off one strip. I'm going to pick, if you can see it, this strip right here, which is really nice looking. So we're going to pull it off like this. And then we're going to start with our one strip. And when the grease is extruded, we know that each strip is 0.25 grams of grease, which is our mass of grease that we're going to use for the test. So here I have a ruler vial that you can see. I put a green sticker on it, so we're going to know that it's green solution. So I'm going to open it up like this. I'm going to fold the grease substrate like this, nice and tight, if we can see it there. And then we're going to put it in the vial. And we saw a picture of this in the slides very briefly. So I'm going to slide it in there and use my tweezers to help me. And I'm going to get it so that it's kind of sitting along the side like that. It's not interfering with anything. And then we have our ruler solution here, which has a nice green square on it. And we know that it's the ruler green solution. So we have a nice dispenser here, so we know we're getting exactly 5 milliliters of solution every time. So we see that puts in 5 milliliters of solution into our vial. And this is where we would begin the process of the sample sitting for 6 hours. So we're not going to keep Grease Thief Thursday open for 6 hours before we run this. So I have another grease sample here that has already been sitting for the interval, and we're going to test that. So,
And Dylan, you can show in the camera that substrate is almost completely loss of grease in that example. Not the one you just did, but the one that's been sitting for a while.
Oh, this. Yeah, so this grease here, this is a used sample. So you can kind of see that the grease is in a dirty condition like that that we're talking about there. And then we see that I forgot to mention, once we prepare the grease too, we're going to want to shake up the vial because we see we have grease kind of sitting at the top. So we have our nice shaker here. And we're going to put it on there so that the solution covers all the grease sample before we start our period of 6 hours. And then over here is our ruler unit. So I can actually take this off here of the stand and we can see the screen. Maybe. Okay, there we go. See, here's our database open. We can see that right there is the green color. So we know that we have a bunch of green samples that we had already run. So this ruler unit is attached to a probe, and the probe is going to sit down in the vial. So I'll sit the ruler here, and I'll take our grease and sit it over here in the rack. And we also have our solution, our vial that has no sample in it. It's just the solution. And we're going to use this to background the ruler so that we know that we're getting a nice background with no peaks in there that don't belong. So we're going to start here. I'm going to go. It's going to be a little bit hard to see, maybe. But I'm going to go and I'm going to click on Run Analysis, which we can't really see. And then our screen is going to come up there, right there, yep. And I'm going to click on Sample, Used Sample Test. So now we're going to enter all of our parameters. We can change our solution type and our volume and all this. So the greases are going to be run at the standard volume for greases. So then first, I'm going to take my calibration vial. I'm going to hit Next. And I'm going to put the probe, take the probe out of its vial, and I'm going to stick it in the calibration vial right here. We're going to screw it on and make sure that the tip of the probe is in the solution, which we can see that it is. So then I'm going to hit Calibrate over here, this green button, which is kind of upside down. So we're going to see our status bar light up here. If we can see it. There it's going forward. See if I can get the webcam to focus on it. There we go. It's almost done. So here we see our calibration run, which is this. This is what a normal calibration run looks like. It always kind of just tails off at the end for the ending voltage, but we see that there are no peaks or anything like that in it, so that we know that that's a good calibration. So we can hit Next, and now it's going to tell us to put in our sample. So what we can do is take our probe out of our calibration vial right here. So we're going to want to unscrew the vial carefully and not do anything to the probe. So we're going to put the lid back on that. And then we're going to wipe the probe with our wipe to make sure it's dry right there. And now we have our sample over here. So I'm going to take the lid off of that, cap off. And then we're going to screw our probe into our vial, and we're going to make sure that we don't get any grease kind of on the tip. This is kind of the most difficult part. You kind of got to screw it in there. We make sure we see that there's no grease on the tip, which you can't really see.
But Dylan,
then-
it does help that the substrate kind of brings that thin grease in and then expands onto the side. So it gives you a lot of room to get that probe in there without getting it fouling on the tip of the probe, right? The grease getting on there.
Yep. Yeah. We want to get it in there without the grease getting on the tip, and then it's not going to foul up the test or anything. So here I'm going to show you the ruler screen again. As soon as we can get the webcam to focus, there, it's going to magically appear. We're going to hit run, which it should. Oh, there we go. Hit it backwards. Here, now the test is going to run. And we have it set to 17 seconds so that we pick up the amine and the phenol and the phenol peaks if there are both peaks present in our sample, which there might not always be. We did that anyway. So here we see our first peak. Yeah, right there. There's like an amine peak, and then we have like a sort of a smaller phenol peak over there with less definition, which that is typical, knowing the baseline of this grease. This is kind of what the spectra, or the graph rather, for that grease looks like. And we can hit save. All right, there we go. Now we can hit all this, go back through this menu here. So now we go back to our database. And that is pretty much it for analysis. How we're going to want to finish it out is take the probe out of the grease like this. And now we'll end up with some grease on the side of the probe. But we see there was no grease on the tip. That's the important part right there, the two electrodes right there. So then we're going to want to wipe this right here. And then just to ensure that there's no contamination, we can use an alcohol wipe. If I can get one out here to clean our probe. And then we want to make sure also that our probe is dry, because the alcohol, the OH group on the alcohol, is another thing that can affect the test. So before we do any more analysis, we want to dry our probe again with another tissue and leave it some time to air dry before we do another sample.
Great. And if you can mute.
Yeah, yep. I will mute.
So thanks, Dylan. And I think, what we see in practice, and that was a helpful demonstration to see what the process is. But I think what we see in practice is that some greases will really dissolve very well on that substrate when you're using the grease thief analyzer to prepare the grease sample in that consistent manner each time. But of course, some greases are going to be aged, or they're going to have contaminants in them or something, and they may not, dissolve as well. Or there may be different chemistries where it's really not optimized to the condition of that particular grease, or really the chemistry of that particular grease. Remember, the solvent that's in the ruler test is really focused on getting that additive separated from the oil. There's a lot of different chemistries, and as greases age, of course, it changes those chemistries. We get things changing, but a lot of times we see our grease samples dissolving almost completely off of that substrate, and getting a very effective transfer. And that's why we really prefer preparing the sample in that way. And of course, we've talked about in this presentation the benefits of being able to add this test to routine grease analysis, or at least in performing studies to better understand optimization of greasing intervals and see where we are with that. Another example that we participated in was with a manufacturer that's using robots. A lot of the Japanese manufactured robots are using greases, while some of the European manufactured robots are using oils in those joints of the robots. So in the FANUC and the Motoman and some of these other ones, there is this opportunity for grease analysis. We had one customer that had hundreds of robots, and they had different responsibilities, let's say, which translates into different cycles. So some robots would be lifting a very low load and moving through a very short movement over a period of time, and maybe an 8-hour shift. And then there was another robot that was lifting up a truck body. So it was very heavily loaded and was swinging back and forth. And then there was another one that maybe had paint, was in a paint booth. So it was making a lot of different movements all day long, 24 hours a day, but it didn't have the same loading. So very different stresses, if you think about it, that we're putting on the grease as a combination of, temperatures, degree of movement and working of the grease and shearing action and so forth, the actual loading that goes into it, temperature changes, contaminants in the environment and so forth, all very different. And yet the guidance for those assets is, regardless of what's going on, you just change the grease out at the same calendar frequency. And what we found by analyzing them and looking at all these different parameters, including the antioxidants, it was clear that there was differences in the aging profiles of those greases. And so that manufacturer was able to go back and make adjustments to that to better optimize being specific to the application for that grease and for the equipment and the way in which it was being used. And that could make a huge difference depending on the application, a huge difference in the cost of operating that asset in terms of downtime and just the maintenance activity of getting the old grease out and putting the new grease in. We really don't want to do that until it's time to do it. And that's the takeaway from this. When we're greasing components, we really want to re-grease that component when it's time to do so. And that corresponds to being at the end of that grease life. And big part of that is that oxidative life, those loss of antioxidants, and getting the grease replenished before it starts to degrade. And one of the best tools to do that we have found is with the ruler tool in the way in which we shared it with you today. So I hope that's helpful. I hope it raises some ideas about how to use grease analysis in the right way to get even more, sophisticated, if you will, in how we treat our assets and take advantage of, that kind of data and that knowledge. And so with that, I want to see if there's any comments or questions that we have, and I can see a few. Okay, there's our participants. I don't know that I see any comments or questions coming through at this point. Anybody have any questions for Dylan or I at this point? Okay, well, we did put this, you got something, Richard?
No, Mindy did just ask a question, actually. She asked if you could hold the greases longer than 6 hours. She said that she's seen people hold it for 24 hours.
Yeah. And again, like sometimes if you're going to hold it for 6 hours, you're into a back shift anyway, so why not hold it for 24? Some of that, I think, goes to, efficiency of process. I don't see any downside to holding it for 24 versus 6. In other words, that the antioxidant isn't going to disappear or degrade or whatever. And I think we did that study. So when we did it, we did hold it for at least 24, I think, Richard, and maybe even longer than that. And what we did is we worked backwards to targeting maybe 90% of the extraction for most greases at 6 hours. So we kind of, target that, and allows us in our operating environment to kind of maybe start the extraction the beginning of a shift and complete it at the end of a shift. I would think what I would want to avoid, and maybe this is Mindy's point, is that you wouldn't want to sometimes wait 6 hours and sometimes wait 24 or, vary it out. You'd want to create within your laboratory, or if you're in the field doing this, some repeatable approach to this, but recognizing that if you do it right away, there is this time of solvency that needs to be acknowledged and recognized, and being consistent is very important, but also giving some, reasonable period of time for most grease formulations that we've encountered to allow the majority of those antioxidants to get in solution and be available for testing. Is that helpful? Okay, thank you, Mindy. I know you guys have been doing this a long time too. I know you guys have some great practices, and I appreciate you being here, asking that kind of question. And I think we certainly learn a lot from each other. So thanks for that question. I appreciate that. Yeah, it's Mindy Vilabla from SGS.
There was one more question. We may need a little clarification, but the question is, how can we insure or get insured for fixed formulation? So we might just need just a little more clarification on that question. I don't quite understand.
So if I was interpreting that, maybe that is saying that we know that there are variations in formulation, and if we don't account for that, since the ruler test is a relative quantification test, it's not an absolute valuation of antioxidants, it's always relative to a reference. If that reference that we are using has changed in terms of the formulation of what is being used presently, that could be problematic. And I'll give an example of that. We had a pharmaceutical manufacturer who sent us two grease samples, and said we would like to do analysis and understand the condition of the grease here. So we did include ruler in the test slate. And when we got the results, we had the sample that was identified as coming from this fan bearing showing a significant response on the ruler graph. But when we went to compare that to the baseline that they sent, it had zero response. And we said, well, that can't be right. You can't go from zero to creating antioxidants in a machine. Therefore, they must have got the labeling wrong. So we came back and we said, we think you screwed up the labeling. And the guy very confidently said, nope, I don't think we did. But if we need to, I will take another sample from that machine and send it to you. And sure enough, it had antioxidants and the baseline did not. And what we found in that case was this grease. Realize that there are a finite number of companies that actually make and formulate grease. There are additional companies that sell grease. So sometimes you get relabeling going on. And what we found in this case is that this was a grease that had a label that identified the product, and it was from a company that didn't actually make grease. And somewhere along the line, they changed suppliers. So the same product, the same named product, had gone from having a very strong antioxidant response to a new formulation that had no antioxidant response. So there was no way to compare them. So there's like two concerns there. First off, that asset owner was concerned that they had, continued to buy the same named product, and suddenly the formulation had zero response to the ruler test. So, the antioxidants that have been there before were no longer in that formulation, and there was no notification and no change in the product name or whatever. But, aside from that extreme example, there are subtle manufacturing changes, blending changes, and so forth as things evolve over time. And these happen without product name changes or even notification to the end users of the greases. And therefore, periodic rebaselining using the newer batches that a customer is getting is a really important thing. And when we see some sudden and unexpected change, a lot of times that's where we'll circle back and say, hey, could you send us the grease, grease tubes you're using now? Let us rebaseline that. Let's see how that formulation is. Because aside from that, there isn't any real way to compensate or offset for those changes. You just really have to know what is the condition of the grease going into the machine, through your auto lubers, through your grease guns or whatever, and then compare the samples that you're getting to that starting point. And because there are formulation changes over time, re-updating and rebaselining those greases is a very important strategy. And so to assist with that, we don't charge to baseline a grease. We just ask the customer periodically, send us those samples, but send us some updated grease so we can get that baseline current and valid. And I hope that was the nature of that question and that addresses that.
You extrapolated perfectly, and that was what he was looking to get.
Okay, good.
I don't see any more questions coming in right now, so I'd just like to thank everybody for joining us today for this Grease Thief Thursday, talking about ruler testing and antioxidants in the greases. And I hope you join us next week. We will be talking about wind turbine analysis and how to get value from the grease analysis to take care of your equipment, and same thing, maintain the life of that equipment to maximize it.
Okay, thanks to Dylan Kletzing, our on-screen talent today, and thanks for Richard for introducing us and helping us through, and we'll see you next week.